Hello and welcome to this homework help video where we're going to talk about a problem that involves throwing an object straight up and having it undergo vertical free fall. We call it free fall because it's being acted on freely by gravity the whole time. There are no other forces at play. So let's imagine that this is our ground and we are going to have a ball, which could be any object, and we're going to throw it straight up, and I'll forego the drawing of a stick figure here, and we'll just imagine that it's going to be tossed straight up into the air, like so. So it's going to have some initial speed, which we call its initial velocity, and then it's going to have a path, which we call a trajectory, which will go straight up, reach some maximum height, where it will momentarily come to rest just for one instant in time because that's where it's changing direction, and then it'll come right back down. Now, for the sake of drawing it come right back down in this figure, I'll kind of show it go off to the right a little bit, but imagine that it's actually staying perfectly vertical, like so. Okay, and we are interested in that maximum height as well as the time it takes to reach that maximum height. And we're also going to approximate gravitational acceleration on the surface of Earth as 10. Okay, now 10 what? 10 meters per second squared, because those units, meters per second squared, are always the units of acceleration in the metric or scientific system. All right, so it's going to go straight up. It's going to accelerate. It's accelerating the whole time. Like I said, gravity is the only thing acting on it. And that's actually a key idea conceptually, because at the very instant it's at the top, it's also accelerating. Even though it's at rest, that doesn't mean it's not accelerating. You could absolutely be accelerating and be at rest. You just won't stay at rest. And of course, that's the case here, because a moment later, an instant later, we'll say, like, or maybe a half second later, our ball is now at a lower point and it has sped up, and it will continue to do so, right, picking up more speed until it comes back to the ground. And in the complete absence of air resistance, it will come back to the ground with a final velocity that is exactly equal to its initial velocity, but pointing the other way, because it will pick up just as much speed on the way down as it lost on the way up. Okay, so what we want to have here is a case of how velocity is affected by acceleration. And we have a couple of key equations. Those key equations are the following. And we can almost get away with just using one, but there's one that's going to be better suited for both parts A and part B, and I'll go ahead and highlight each of them. So in part A, we're going to have an equation that involves the way that velocity changes with time when there is a constant acceleration. So the equation looks exactly like this. Okay, so the way we would read this equation is we would have the velocity is the output, and that's the one over there on the left. Okay, so this is the instantaneous velocity, or just the velocity at any moment in time. Instantaneous velocity. And this is the initial velocity, which is often something that right? You're given that's part of your initial conditions that you are able to ascertain, all right? So velocity, I'll put up here, initial. Okay, and then the A, no surprise, is the acceleration. In our case, that is going to be in magnitude 10. Now, one thing is a lot of students will ask me, oh, you made a mistake, professor, you forgot to put the negative on it. Well, no, that's because as a vector, gravitational acceleration, and vectors have direction, by the way, it points downwards, and in a typical vertical coordinate system where up is positive, then we call down negative. But if I'm just talking about the value of g, then it is 10, right? That's what's called its scalar value, or its magnitude. Now, when we write this equation, though, we have to acknowledge that the object was thrown up, right? So its initial velocity was up, and so that 26 meters per second, if it's in the positive direction, means that g has to be in the negative direction. Okay, so here you can think of it as just the absolute value, but if I was to add that to our figure, we'd have, with the appropriate directions, we'd see g goes like this. Okay, and often you actually put little arrows on top of the letters to denote that they're vectors, but in this class we're not really going to be doing that very much, so I'll just leave those off. Okay, but still, despite that extra little arrow over the letter or not, we can see that there indeed is an arrow showing the initial direction of the velocity, and the constant unchanging direction of the acceleration. And if I was to show the velocity at the top, there'd actually be nothing to show because it's just 0 at the top, right? For that one instant in time. And so I bring that all up because over here, this value for acceleration is just going to be gravity. All right, acceleration. And so in our case, because you can use this equation for other constant accelerations, like pushing on the gas on a car and then saying that the car is accelerating constantly, usually in that case, right, the acceleration isn't as reliably constant. This is the cleanest case of constant acceleration, and it's only as clean as much as you ignore air resistance. But it's still a nice system for considering constant acceleration. So here, A is going to be negative 9.8, okay? Because again, I have to pay attention to the negative here because I'm going to put a positive value in for V naught right there. All right, and then t is none other than time, and that's actually what we're solving for. So actually, let's switch over to red to show that this is our particular variable or value of interest, okay? And the idea here is that this is a function, all right, as well as an equation to kind of, depending on the context, function, equation, call it what you want. And I say it's a function because it's a function of time. So I think of this as velocity, instantaneous velocity, as a function of time. You input time, you get out velocity. Okay. However, right, that's not what we want here. Instead, we actually know a velocity and we want a time, right? Because we're told, or rather we're asked, how much time does it take for the ball to reach the top of its trajectory? Okay. So let's go ahead and use our value here of 26 meters per second. Okay. And we'll go ahead and plug that in and then see what we get for our time. Okay. So we're going to plug in for V naught a value of 26 meters per second. We're going to plug in for our A, I put 9.8 out of habit, right? And that's because a lot of times we use that. However, in this problem and pretty consistently in physical science and with Hewitt's textbook, it's going to be rounded to 10, okay? And so here we're going to put 10 meters per second squared. So that's a rounding. And I'll change it over here as well to be consistent. So let's do that. All right, so negative 10 meters per second squared. And then finally, we'll have that variable for t, and that's exactly what we're going to be solving for. So we have to rearrange this equation, which we can do before or after we plug the values in to solve for t. In this case, as it's written, it looks like I'm already plugging in the values, right? I've started doing that. However, you might be thinking, but wait, there's a missing value, right? What's going on here with this v, the instantaneous velocity? Well, this comes into reading the problem and the word problem aspect of mini physics. Many things in physical science, and in particularly physics here, which is this would be classical physics or mechanics or kinematics, okay? And what we're looking at is that at the very top of the trajectory, the ball is momentarily at rest, right? Because if it reaches the top, that's an instant where its velocity is 0. So we actually know v. We know that v is 0 meters per second, okay? So right there, and often I don't put the units on when there is 0 because it doesn't make any difference. And so there we have our equation, and we can just pretty easily solve for t. And we can see that it's a good thing that we have that negative on the acceleration, because if we didn't, then we'd have the negative time, which is physically impossible. So this is the way it has to work, which makes sense because there's no way that you could go from starting in motion and then sometime later being at rest, unless your acceleration was a deceleration, as we call it in common language, because you have to be slowing down, right? And that's exactly what's happening here. The ball is slowing down as it moves upwards, right, until it reaches its maximum height. So then we can go ahead and just solve for t, and I'll leave that up to you. And you can obviously work with different values when you solve this problem for yourself. Now, I said that there was going to be another key equation, and so I'll go ahead and put that over here. And we'll actually label this column the algebraic work. All right, so algebraic steps. All right, and that's going to go ahead and also be for A, because we talked about the whole time. And I'll just highlight the fact that, as I said, you would then solve for t. So we'll say, and then solve for t, time t. Okay, and that would be your answer, as you can see, and the units are going to be in seconds. Okay, so on to part B and the key equation that gets us started with that one. Now, what is that key equation? It is one that, again, involves constant acceleration, but this time it relates constant acceleration to distance, because we are asked to find the height of the ball, right? And again, without air resistance, because that's been a big overriding assumption throughout the problem. And it's going to be, how high does it reach? What is that maximum height it reaches from the ground? And so in our figure, it would be this distance right here. And we're not so much interested in being positive or negative. We're just interested in its magnitude. But if it's measured from the ground up, that would be positive with the way we've been sticking with our coordinate system, which I actually did want to put on here. I really like to put my coordinate system in my figures because I'm calling positive y the upwards direction. Okay. Y often being associated with vertical, and then x being associated with left and right or back and forwards. Okay, so part B, find the height. Okay, so solve for h. How do we do that? Okay, so our equation here is an equation that's going to relate not time. Now we could. There's an equation that actually nicely relates acceleration and velocity and time, or rather relates distance and velocity and time, and particularly initial velocity, not instantaneous velocity. And that one's fine, especially if you're interested in how far you make it in a certain amount of time when you're experiencing constant acceleration like free fall. That'd be great for not parachuter, because that's definitely not free fall, and that's actually approaching a zero acceleration at terminal velocity. And before then, it's a changing acceleration, which wouldn't apply to this system. That's neither here nor there. But if you did have a freely falling object, like dropping a rock off the side of a cliff and ignoring air resistance or saying it's negligible, which is practically ignorable, then we'd have a case where that rock is going to speed up, and we want to know how far it's traveled after 3 seconds of being dropped. Well, that would be a case where we relate distance and acceleration and time. But we're not asked for that, right? We just need h. So all that to say that the equation that we want is this one right here, which is going to have our instantaneous velocity, and switch back to black, so v squared, and then our initial velocity, so kind of looks similar as before, except there's squares on them, okay? And deriving these, you can derive them algebraically, you can understand them with graphs, but we're not going to get into the background here, rather just the process. And then plus 2a, and then this part here in parentheses is actually going to be the y final minus y initial. I'm going to go ahead and write that, but in this case, it's going to significantly simplify to just h, because these are two coordinates, just where you started along a coordinate, along a line. This is all one dimensional, so you just single directional path. You can either go forward or backwards, right? Just straight up, straight down, right? As I said before, this is just strictly vertical free fall. And that's in comparison to what's called projectile motion, which is like launching a cannonball or something, because then it's two-dimensional, okay? And we can deal with that a little bit, but then it gets to be a little complicated trigonometry. So here, we just have y final, y initial, okay? So this would just be where you start in the vertical direction and where you end in the vertical direction. Now, where do you end? Well, you end where whatever is your point of interest. In this case, we're interested in finding the maximum height. So that means our y final, and here I wrote it back. I said it backwards, but I wrote it correctly. I said this is where you start, but of course, some of you were like, well, there's an F there. Is he saying it right? I was not. This is where you end, and this is where you start. So it's your final position minus your initial position. And so if I was to add that over here, it would simply look like this. And it's not a big change or addition. We would just say that if we had a coordinate system, we would call the ground 0, because that's our initial height, and then we call our final height, well, h. See? And then h is just the displacement between those 2 points. And so then you see that the equation simplifies in cases like this, where you're just interested in a single distance, all right, to 2a h. Okay. And, to be specific, before, I had a really general case, and I left it there, that in the actual algebraic steps, I talked about plugging in a value for gravitational acceleration rounded to negative 10 meters per second when the direction matters. Well, you could actually, kind of stick with the key equation idea and replace that a with g. So often you'll see an equation that looks a little bit like this, where it's the a has been actually directly replaced with g, and it might even be written like that. Because then you have an equation that's ready to go. It's specific to free fall rather than more generally to constant acceleration, but certainly it would be another case of a key equation, just a little bit more of a customized one. Now, what the heck are we solving for? Just to get us back to grounded. What are we doing? Well, we're just going to solve for h, okay? So as written, the equation really doesn't solve for anything precisely. One thing you can do to clean it up is to take the square root of both sides. Say if you wanted to find the velocity at some instant. Now in this case, you wouldn't you don't need to find the velocity at the instant because you know it, right? We know that v is 0, right? Because we're interested in it getting to the top where it's momentarily at rest. But if you wanted to find out how fast it's going when it's halfway to the top, well, then you might want to solve directly for v, and you know h rather than solving for h. And in that case, you just take the square root of both sides and directly solve for v. That's kind of the way the equation's set up. But we're going to rearrange it to solve for h. All right, and doing that is kind of nice because we don't have to take the square root. So we're going to have over here, we would have our v squared becomes 0 squared, okay, which is just being consistent, just 0, right? If I leave the units off and when I say it's 0, I might as well leave off the square because it doesn't make a difference. And then over here, we'd have our 26, plug in the numbers, my example of numbers, minus, and here I've essentially factored out the negative. Right here, I left it in the general form with the plus, and I know I'm paying attention a lot to the sides, but they could trip people up pretty easily. And so pay attention if you do have a hard time with remembering where to put the negatives or getting easily confused if it's a negative or not, because in this case, right, this is totally general. And then when you plug in the specific case of gravitational acceleration, which then is going to be negative, that's why in parentheses it shows up as negative. But here, when we've rewritten the equation, we've essentially factored out that negative. And so then go back over here, then we just have 2, and then our 10 meters per second squared, because like I said, the negative's in front, and then there's our h. And then we just solve for h. All right. There we go. And solve for the max height h. Okay, now solving for the max height h, there's nothing sacred about that. This equation doesn't always give you the max height. It just gives you the max height because that's 0, right? Because being 0 only happens for an object that's launched upward at that one point, which is the point of maximum height. Okay, so it's just matching up that information. Okay, so here it works out great, and we'd simply be able to solve for h, and it would represent the max height. Okay, well, I hope this homework help video has been helpful. Thank you so much for watching.